Okay, so this is finals review packet day 2. Again, just a reminder, if you want to know 100% certainty what's on the test, you need to download the actual exam outline. Couldn't think of the word outline. Download the outline from the course website, okay? And that's true for both on-campus students and online students. Both online students and on-campus students have an outline posted for your exam. All right, so let's go through some problems today for day 2 of the packet. 21.82 grams of sodium reacted water. How many moles is this? All right, when we're doing this conversion of grams to moles, do we use Avogadro's number? What do we use? You use molar mass, right? So where is that from? From the periodic table. So 21.82 grams Na. Does grams go on bottom or on top? Right, grams goes on top, bottom, 1 mole goes on top. And then what goes here? It's molar mass, so it's 22.99. So this is going to be really close to 1 mole, 21.82 divided by 22.99. All right, my calculator tells me 0.949108308. Can I keep all those decimal places? No way. Why? That's way more accurate than the number I actually measured, right? So what's my final answer? How many sig figs do I keep? 4 sig figs, so that would be 0.9491, and my unit would be moles, right? Is this 0 significant? No, it's not. Why is this 0 insignificant? It's to the left of a decimal place, right? Because I could rewrite this. That 0 is not necessary. I could just write it as 0.9491. I also could write it in scientific notation, 9.491 times 10 to the negative 1, right? That 0 is not significant. All right, any questions on number 1? All right, let's do number 2, nomenclature. Name the following. What's the name of AlCl3? Aluminum chloride. All right, what's the name of Li3N? Lithium nitride, good. And what's the name of MgO? Magnesium oxide, good. Are these compounds formed from monatomic ions or polyatomic ions? These are all monatomic ions, right? Because that's a monatomic ion, monatomic. These are all monatomic ions, right? We don't have any polyatomic ions. All ending in "ide", right? These are all monatomic ions. Questions about number 2? We had 100% so far? All right. After 2 problems, everybody's got 100. That's good. That's good. All right, let's go on to the next one. Just go ahead and give myself some more space here. Okay, iron 3 chloride reacts with calcium hydroxide. Write a balanced chemical reaction. So, what's the formula for iron 3 chloride? FeCl3, good. And what's calcium hydroxide? CaOH2. What kind of reaction is this going to be? Double displacement, right. So, I have my 2 reactants, and the cation of the first gets together with the anion of the second, and the cation of the first gets together with the anion of the second. So if this is iron 3 over here, is it still going to be iron 3 over here? Yes. So Fe3 plus getting together with hydroxide, OH minus. So what's the formula for the product number 1 going to be? FeOH3. That's an E, by the way. It looks like a C. It's an E. And my other product, calcium and chloride. Right? What's the formula going to be there? CaCl2. Okay, so let's write it a little bit bigger so we can balance it now. All right, let's balance this now. Do we need to make a reactant product table, or can we do it in our heads? Want to make a table? Yes. Okay. Let me give myself some room here. Okay. So if we're going to make the table, reactants on one side, products on the other. All right, we've got Fe. We've got 1. Chlorine, we've got 3. Calcium, we've got 1. Oxygen and hydrogen, how many do we have? 2, right? That's a little tiny 2. 2, right? We're distributing that 2. Now we're going to write everything in the same order over here, right? So that we can read straight across. So Fe, Cl, Ca, O, and H. So iron on the product side, we've got 1. O's and H's, we have 3. Ca, we've got 1. And Cl, we've got 2. Okay, so you can start wherever you want. It really doesn't make a difference where you begin, okay? Because you're going to end up doing the same thing regardless. Moving the mouse out of the way. So let's do the O's and H's first. Can I turn a 2 into a 3 or a 3 into a 2? No. What's the least common multiple of 2 and 3? 6. All right, so if I want to turn this to 6, what should I put right here? A 3. But I've got to distribute it to everybody. Right? So 3 times 1 is 3. 3 times 2 is 6. 3 times 2 is 6. Now let's go over here. What do I do to turn a 3 into a 6? A 2. Right? But I go ahead and distribute it to everybody. So 2 times 1 is 2. And then 2 times 3 is 6. And then 2 times 3 is 6. All right, now let's do the chlorides. Same problem, right? A 3 is not turned into a 2, or a 2 is not turned into a 3 by a whole number. But what I can do is turn them both into what? 6. So if I'm turning this 2 into a 6, what number goes here? 3. I've got to distribute it to everybody. So that becomes 6. That becomes 3. And now to turn this 3 into a 6, what do I need to multiply? 2. That becomes 2. That becomes 6. So now reading straight across, 2 irons on both sides, 6 chlorides on both sides, 3 calciums on both sides, 6 oxygen, 6 oxygen. So my final coefficients are 2, 3, 2, 3. Questions on number 3. Questions on number 3. So if you get stuck, let's say you're doing your reactant product table and you're just like, it won't balance. Number 1 thing that I would recommend is just erase it and start fresh. And start with a different element that time. Okay, because maybe you just accidentally forgot to distribute something. So if you're going in circles and you're not getting into balance, the other thing you can do is go back and check your formulas, right? Because if your formulas aren't correct, then your table won't balance. So if you're getting stuck and you've tried starting from scratch, make sure your formulas are correct too, right? Because if your formulas aren't correct, then you could be going in circles for a very long time. Questions on 3? All right. let's go on to number 4. We'll just go ahead and move these down as well. Okay, draw the Lewis structure for HCO2 minus. So what do we need in order to draw a Lewis structure? What information must we know? We need to know the number of what? Lewis structures represent the valence electrons, right? So we've got to calculate that. So let's calculate that first. Hydrogen, there's 1 hydrogen here. And how many valence electrons does hydrogen have? 1, right? It's in group 1. There's 1 carbon here. How many valence electrons does it contribute? 4, right? And there are 2 oxygens. How many does each contribute? It's in group 6 of the periodic table. 6. Now this is HCO2 minus. This has got a minus charge. So I add 1, right? Right? Because this is a negative, that means it's gained extra electrons, right? If this were HCO2 plus, what would you do? Subtract. But because this is HCO2 minus, you add 1. Okay, so now we just add all those up. So 16, 17, 18. Okay. So now we know number of valence electrons. Now we're going to make our skeleton. Who goes in the middle? H, C, or O? Carbon goes in the middle. Why? The least electronegative. And what's the rule on electronegativity? The closer you are to, who's the most electronegative? What's the grade you least want in this class? Fluorine, right? Fluorine's the least electronegative. I mean, the most electronegative, most electronegative. Right? That's the one you want to avoid being in the middle. It's a grade you want to avoid in this class, right? Most electronegative definitely can't go in the middle. Least electronegative goes in the middle because remember, if you're electronegative, you're not good at sharing, right? So you're not going to put an element who isn't good at sharing in a position where it has to share. So carbon's least electronegative. Hydrogen can't go in the middle. Why? Hydrogen forms how many bonds? Just 1 bond, right? Because it's only got 2 valence, 1 valence electron to deal with. All right, so carbon goes in the middle. Now, does it matter if I put HOO or OOH or HOO? Does it matter how I orient that? No, it doesn't. So whatever makes you happy. All right, we've got 2 oxygens and 1 hydrogen. So let's just do hydrogen, oxygen, oxygen, just for fun. You could have oriented it in a T, in a sideways T, however it makes you happy. Each one of these sticks represents how many electrons? 2. 2. So 2, 4, 6 are represented. So I've got 12 more to go. All right, who gets an octet first? The O's. Why do I not need to put dots on hydrogen? Hydrogen only needs 2 to be satisfied, which it already has, so we're good. So now we just put dots. 2, 4, 6, 8, 10, 12. All right, that's all 18 electrons. Am I done? Can I just stop here? Why? What's wrong with carbon? It doesn't have an octet, right? It only sees 2, 4, 6. So what do I need to do? The last 2. I'm out, right? So what do I do? Right. So we're going to, instead of having a pair just sitting there doing nothing, it's going to come be a double bond. Okay, now everybody's got an octet. What do I do because of its minus charge? Put brackets around it, and then what? A negative in the corner. Now, does this have resonance? Yes, what is resonance? More than one way, right? So what's the other resonance structure look like? just have the double bond over here, right? Are we good on number 4? Questions on number 4? So is there resonance? Yes. There it is. All right. Let's move on to number 5. I'm going to give myself some space here in case we need to make some reactant product tables. Okay, we're going to write balanced equations and state the type of reaction. So hydrogen peroxide, and I've given you its formula, H2O2, breaks down into water. What's that formula? H2O. And what's the formula for oxygen gas? O2. Why is it diatomic? Oxygen is one of 7 elements that are diatomic as gases, right? Make my arrow a little bit smaller here so we don't squeeze in that coefficient in there. Okay, let's make our reactant product table. So hydrogen's got 2, oxygen's got 2, hydrogen's got 2, oxygen's 1 plus 2. So what should we do? One plus 2, that's 3, right? Okay, that's kind of challenging to deal with. What if I turn this number into, say, 2? Then I could add this up to 4. Is 4 a multiple of 2? Yes. So how would I turn this into a 2? Which one do I multiply by? Which one do I multiply first? Is it H2O or O2? Okay, I want to turn this into a 2, so what do I need to put in front of H2O? A 2, and then I need to distribute it. So 2 times 2 is 4, and 2 times 1 is 2. So now this sum is 4. So what do I need to do on the other side? 2H2O2, right? 4 and 4. So 4 hydrogens on each side, 4 oxygens on each side. Do we agree on 5, part A? All right. Let's do the next one. Oh, we didn't say what type this is. What type of reaction is that? It says state the type of reaction. Is what? It's not combustion. Decomposition, right. Because you've got one reactant, multiple products, right? That's decomposition. Okay, let's do the next one. Aluminum metal. What's the formula for aluminum metal? It's just Al, right? When you see the word metal, that should think, okay, straight from the periodic table. Combines with oxygen. Now this is oxygen gas. So what's its formula? O2. Because when you see oxygen by itself, right, straight up oxygen, you need to think, okay, that's got to be oxygen gas. And we're forming, I haven't told you what the product is, aluminum oxide. What's the formula of that? Al. Aluminum's Al, 3 plus. Oxide's O2 minus. So what would that be? Al2O3, right. This would be solid. This would be gas. This would be solid. Okay. So we're going to make a reactant product table for this one. Al, O, Al, O. Aluminum, I'm beginning with 1. Oxygen, I'm beginning with 2. Aluminum, I'm ending with 2. Oxygen, I'm ending with 3. So I would not do aluminum first, just because aluminum's coefficient is 1 here, which means I can turn it into any number I want, right? Because any number times 1 will give me that number. So let's do oxygen first, because it's clearly going to be the more taxing problem, right? The same issue we've had in the past. Can I turn 2's into 3's or 3's into 2's? No, but I can turn them both to 6. So what do I need here? How do I turn this to a 6? A 3, right? 3 times 2 gives me 6. How do I turn this to a 6? 2, but I've got to distribute it to everybody. 2 times 2 is 4. 2 times 3 is 6. Now, what do I do for aluminum? 4. Now for type, there are 2 answers that would work. What's 1? That's one of the types that would work. What? I think you said it correctly. Synthesis would work. Yep, actually there are 3. I forgot about synthesis. Synthesis would work. It's not single displacement because this isn't a compound. We're not replacing one with another. Remember at the beginning of this semester, I told you reaction with oxygen. What's that called? Combustion. I would have accepted combustion, right? That'd be combustion of a metal. If you set it on fire, you would have this reaction take place. And then there's one more. One more. I'm going to erase my reactant product table. See if I can help you. What kind of reaction is this? It's redox, right? Now you have to have both. Aluminum's going from 0 to +3, right? That's oxidation. Oxygen's going from 0 to -2. That's reduction. So I would have accepted any one of those 3. That's a redox reaction. That's a combustion reaction if it occurs really quickly, right, if you set it on fire. And that's also synthesis. So I would have accepted any one of those 3. Questions on number 5, part B? All right. Let's move on to number 6. I wonder if the recording can pick up the audio from that, whatever video they're watching. I don't know how sensitive the microphone is. All right, let's do some naming. Let's just go ahead and move this up. It's too high. Okay, so CUS. CUS. What's the name of this? Ugh. I want more space. There we go. What's the name of CUS? It's not copper sulfide. You're close. There's something missing. Right, it's copper 2 sulfide. Why is that 2 necessary? Why do I need that 2? Because copper can what? It can form ions, cations of more than one charge, right? We've got to specify which one. And how did I know it was copper 2? Well, if sulfide is -2, and the subscript here is 1, that means this one must be +2. Right? Got to work backwards. Uncrisscross. All right, MgSO4. Something I'm hoping to avoid. What is the name of MgSO4? Magnesium sulfate. Good. If you go into labor early, that's something that they give you in your veins. I had it with the twins. It was no fun. So I'm hoping to avoid that a lot. All right, what's the name of PbBr2? Lead 2 bromide. Good. And what's the name of CuCl? It's not just copper chloride, it's copper 1, right. Remember, copper's a transition metal, chloride's -1, this is a 1-to-1 ratio, so that means this must be +1. Right? In other words, we're uncrisscrossing them. If you forgot that Roman numeral, I'd probably only take off half a point, if everything else is correct. If you got something else wrong, obviously you lose more points. But if all you did, if you said copper chloride instead of copper 1, I'd take off half a point for that. That's not a big problem, right? It's just a minor mistake. Are we all good on number 6? Nomenclature. All right, let's do number 7. Magnesium metal. When you see the word metal, that should tell you something specific. What? Actually, I'm going to move this up. I thought I had enough room, but I don't want to be bending over. Magnesium metal. When you see the word metal, that should tell you what's its formula. It's just straight from the periodic table, right? So it's just what? What's magnesium's symbol? Mg. Reacts with copper 2 chloride. It's going to be solid. Copper 2 chloride. We just did that one a minute ago or something similar. Well, no, we did sulfide. So copper 2 chloride would be Cu what? Cl2. That'd be aqueous. Okay, what kind of reaction is this? Right. Make sure you put both words. I remember people getting points lost when we did this chapter. They just write single or double, right? It's not just single displacement. Okay, so the metal becomes the new what? So does the metal become a cation or an anion? And look at the periodic table. Can magnesium become an anion? Is that possible? Magnesium's in group 2. Do metals ever become anions? No. So this metal is going to become a cation. With what charge? What's the charge on magnesium cation? +2. And this metal that's now a cation is going to get together with what? The cation or the anion? The chloride, right? Because if it got together with copper, that'd be 2 cations. That doesn't make sense, right? You have to have a positive and a negative. So it would be chloride that it's getting together with. Chloride has what charge? Minus, right? So when we crisscross those, we get MgCl2. And that would be aqueous. What's our other product going to be? Just plain old Cu, right? Okay. Do we need to make a reactant product table? No, we're lucky. It's already balanced. Life works out nicely sometimes, right? If you want to go through and put ones in all those blanks, you can, if it makes you happy having something there. All right, but you do not need, oops, got a little bit too excited. You don't need to balance this. When you write it as is, it's already balanced. Woohoo! Is this redox? Let's ask ourselves this, because I said single displacement. Let's ask ourselves if this is redox. Good review. Magnesium, what's its oxidation number here? 0. Right, that's a pure element. All right, what about here? Let's do CuCl2. right? This is the contribution. This is the oxidation number. Are there any rules for copper? Copper's in the transition metals. Are there any rules? No. But we have a rule for chloride. Group 7 is usually -1, right? There are 2 of them, so it contributes -2. So what must copper be? +2. So +2, -1. Let's do magnesium chloride. This redox is definitely on the final. Let's see. Magnesium's in group 2. Do we have rules for group 2? We do. What is the rule for group 2? It's +2. So there's 1 of them, so it contributes +2. So what does that mean? The contribution of chloride needs to be -2, so that this can add up to 0. So what does that mean chloride is? -1. Right. So this is +2. This is -1. And what's copper solid? 0. All right, so we can ask ourselves, do I have change in oxidation numbers? Yes, I do. Right? Chloride is not changing, so it's spectator. Who cares? Magnesium's going from 0 to +2, and copper's going from +2 to 0. So what happened to magnesium? Did it gain electrons or lose them? It lost, right? So that's oxidation. Remember Leo? That's oxidation. And copper went from +2 to 0. So did that gain or lose? That's the GER, right? Remember, lose electrons is oxidation, gain electrons is reduction. So just for good review, what's the oxidizing agent? Copper, good job. Anything that gets reduced is the oxidizing agent. And then what would the reducing agent be? Mg, good. All good things to review. This is also redox. So if you wrote redox as the type, I would have accepted that as well. That'll help you with your lab report that's due Friday. All right, moving right along. Propane is a common fuel used for cooking and home heating. What mass of O2 is consumed? What did I do with my marker? And the combustion of a 1 gram sample. What did I do with it? Oh, there it is. Okay, so first thing we got to do is we got to write an equation. So we've got C3H8. What state is propane? Solid, liquid, gas, aqueous, who knows? Your propane tank has what in it? Liquid? A lot of times it's gas. And this is combustion, so what is it combining with? O2, what state would that be? Gas, right? So we're going to be producing what 2 substances? H2O. And what state's that? Well, when you burn something, do you see a puddle? It'll be gas, right? Because it's vapor. And what other substance? CO2. Also gas, right? Okay, let's balance this. Reactants, products. So CHO, CHO. 3, 8, 2, 1, 2 plus, oops, just, excuse me, here it's 1 plus 2. Okay, let's balance carbon. So what do I need to put to balance carbon? What goes here? 3. And we distribute it to everybody. So 3 times 1 is 3. 3 times 2 is 6. What do I do to balance hydrogen? 4, right? 4 times 2 is 8. 4 times 1 is 4. So this sum is 10. Is 10 a multiple of 2? Yes. So what do I do? A 5, right? So that becomes 10. 3, 3, 8, 8, 10, 10. All right, so that's the first part, right? Because I have to have a balanced equation before I can have anything to do with figuring out the masses that I'm dealing with here. So that's step 1, write a balanced equation. Now we're going to do some calculations, right? I've got a 1 gram sample, and I want to know what mass of O2 I'm using up. So what kind of calculation would this be? There's only one way I can do this. Can I just say, oh, it's 1 to 1, ta-da, 1 gram. You wish, right? What kind of calculation is this? Starts with S. It's stoichiometry, that's right. All right, so let's go through it. 3 steps. First step is what? Grams to moles, right? Okay, so I've got 1.00 grams C3H8. Do I use molar mass or Avogadro's number to convert grams to moles? Molar mass. How do I get that? C3H8 isn't on my periodic table. Right, you gotta add them. So that's a side calculation I'd have to do. So let's see. 12.011 times 3 plus 8 times 1.008. I got 44.097. So 1 divided by 44.097. We're going to carry out extra digits, right? Because we're going to round at the very end. So that gives me 0.022677 moles. C3H8. What's step 2 of stoichiometry? Mole ratio, right. And where does the mole ratio come from? The coefficients of the balanced equation. Good. So mole number here just goes straight down. So 0.022677 moles C3H8. For every 1 mole of propane that I use, how many moles of oxygen do I use? 5, right. So moles of propane cancel. So multiplying by 5, dividing by 1. 0.113386 moles O2. What's step 3? Convert back to grams, right? So moles back to grams. So take my number that I just got, 0.113386 moles O2. 1 mole of O2 has a mass of 32 grams, right? Because each oxygen 16, 16, 16 is 32. So times 32. That gives me 3.628364741. Is that my final answer? How many sig figs can I keep? 3. So my final answer is what? 3.63. And what are my units? It's grams, right? Questions on number 8. Questions on 8. All right. Let's go on. Is it useful for you to have done these in advance so you can go through the work as we're going over these? Okay. Balance the equation. So we need to make a reactant product table. C, H, O, C, H, O. 2, 6, 2, 1, 2 plus 1, 2. All right, how do we balance carbon? How do we balance carbon? Coefficient of 2, right? So 2 times 1 is 2, 2 times 2 is 4. How do we balance hydrogen? 3. So 3 times 2 is 6, 3 times 1 is 3. This sum is 7. Is 7 a multiple of 2? No. So what do I do? How do I turn a 2 into a 7? I say to myself, okay, 2x equals 7. So x must be what fraction? 7 over 2, right. Are you ever going to have 7 halves of a molecule? No. So what do I do to get rid of that fraction? Multiply everybody by 2, right. So that makes my coefficients 2, 7, 4, and 6. Do we agree? Is this redox? Is this a redox reaction? A lot of reactions that we've talked about this semester, because we could definitely classify this as combustion, right? For sure. Is it redox? Let's review. Let's check. C2, H6. All right. Do we have any rules for carbon? Carbon's in group 4. No rules for carbon. Do we have a rule for hydrogen? We do, right? This is the oxidation number. This is the contribution. All adds up to 0. What's hydrogen? Plus 1. So it contributes what? Plus 6. What must the contribution here be? Minus 6. And there are 2 of them. So what does that make carbon here? Minus 3. So minus 3 plus 1. What about O2? What's its oxidation number going to be? 0. Right. Let's do CO2. We don't have any rules for carbon, but we do have one for oxygen. What is it? 9 minus 2, so it contributes minus 4. So what must carbon be? Plus 4, and there's only 1. So this is plus 4. This is minus 2. And then in H2O, hydrogen's always plus 1, oxygen's always minus 2. So now we just need to compare before to after and ignore anybody who's not changing. So hydrogen doesn't change, right? So I can ignore it. I can just pretend it's not part of this process. Oxygen is minus 2 in both of these, so it really doesn't compare which one I look at. So carbon's going from minus 3 to plus 4. Oxygen's going from 0 to minus 2. So is this redox? Yes, it is. Which step is oxidation? Carbon's getting oxidized, right? It's minus 3 to plus 4. That's a big loss. Who's gaining? Right, that's the reduction. I'm making special effort to review redox because you haven't been tested on redox yet, right? This semester, the way our exams fell, you weren't tested on redox on exam 3. Some semesters it is on exam 3. This semester, because of where the breaks and everything were, it wasn't. So that's not something you've been tested on yet. All right, let's do some Lewis structures. ClF4 plus. So first we have to calculate number of valence electrons. How many valence electrons does each chlorine have? 7. How many does each fluorine have? What do I do for that charge? Subtract 1. Wait, 4 times 7? Is that 28? Yes. Sorry. Okay, so what's my sum? Okay. Now, who goes in the middle? Chlorine and fluorine are both pretty electronegative, but one is clearly not going to be in the middle. Fluorine's definitely not going to be in the middle, right? It's way too electronegative. So chlorine goes in the middle. A lot of students, if I say, why is chlorine in the middle? They'll say, oh, so it's symmetric, right? That's not the reason. Okay, it does happen to be symmetric, kind of, but that's not the reason, right? So 2, 4, 6, 8. Right, 2, 4, 6, 8. So how many do I have left now? 28. Okay, what's going to happen? Who gets octets next? The F's, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've got 4 left over. What do I do with them?
I think your 28 is supposed to be a 26.
Yeah. Oh. Yeah, you're right. I got 2 left over. Thank you. What do I do with those leftovers? They go on chlorine, right? And then what do I do to account for the charge, to show it? With brackets and a plus. Now, is this an exception to the octet rule? Yes. What is it called when chlorine sees more than 8 electrons? Remember what that's called? It's called an expanded what? Octet. Right, that's an expanded octet. When you see more than 8 valence electrons. All right, I'm going to pause the video so we can take a mental break since we've been going for an hour now. All right, let's go over some more of these. So this was the next one in the list. 2.59 grams of iron metal reacts with 3.3 grams of oxygen gas, produces iron 3 oxide. So the first thing we need is a what? Balanced equation. Iron metal has what formula? Fe. And oxygen gas is what? O2. It produces iron 3 oxide, so what's that formula? Fe2O3. That's rust. All right, let's balance this. Reactant, products. Fe is 1, O is 2, Fe is 2, O is 3. So let's put a 2 here. 2 times 2 is 4, 2 times 3 is 6. Let's put a 3 here. 3 times 2 is 6. And then a 4 there. What kind of reaction is this? Just as a review. What type of reaction is this? There are 3 answers I'd accept.
Combustion.
Combustion would work. What else?
Synthesis.
Synthesis would work. What else?
Redox.
Redox would work. Right? So I would accept either one of those 3. But that's not what the problem asks. The problem asks, what's the theoretical yield of this product? And I have 2.59 grams here and 3.3 grams here. So can I do stoichiometry once, or do I have to do it twice? Gotta do it twice. Lucky, lucky us, right? So I'm actually gonna give myself some more room. I'm gonna rewrite my problem up here so I can have room. This is what I'm interested in. 3.3 grams, 2.59 grams. All right, so I've got to do the stoichiometry times 2, right? Because I have to figure out which substance is the limiting reagent. The problem even asks. It's theoretical yield and which says the limiting. So here we go. We got to do it for iron. All right, grams to moles. So 2.59 grams times iron's like 55 something. 55.845. 55.845 grams per mole. So we do some division. 2.59 divided by 55.845. Carrying out extra decimal places because I'll round at the end. That gives me 0.04638 moles Fe. What's my next step? Mole ratio, right? For every 4 moles of Fe that I use, I produce 2 moles of Fe2O3, right? So times 2 divided by 4, or just divided by 2, right? Because 2 over 4 reduces to 1 over 2. So divided by 2. That gives me 0.02319 mole Fe2O3. What's my last step? Convert back to grams. So 55.845 times 2 plus, I get 159.69 grams per mole. So times 0.02319, 3.7032111. So what does that round to in terms of sig figs? 3.70. Am I done? Nope, I'm only halfway there, right? Because I did it for iron, now I gotta do it for oxygen. Gotta repeat this whole procedure. So 3.3 grams times 32 grams per mole O2. So 3.3 divided by 32. Carrying out extra decimal places, 0.10313 moles O2. Forgot to cancel out my units there. All right, mole ratio time, right? 3 moles O2 for every 2 moles Fe2O3. So times 2 divided by 3, times 2 divided by 3, gives me 0.06 875 moles Fe2O3. I don't need to recalculate the molar mass because it's going to be the same. So when I do that, the calculator gives me times 159.69, 10.9786875. How many sig figs am I keeping here? 2. So what does that round to? 11. Units or grams. So what's the theoretical yield? 3.70 or 11? 11 is not the theoretical yield, right? 3.70 is the theoretical yield. And the limiting reagent is what? Fe, right? And the excess reagent would be O2. Questions on number 10? Right. When you have information about more than one substance, that's a limiting reagent problem. Got to do it twice in terms of your stoichiometry. Okay. That was number 11, not number 10. Formula writing. Okay, what's the formula for calcium? Calcium has what charge? Ca. We're doing it. We're breaking it down as the cation and the anion. So calcium Ca2 plus. What's carbonate? CO3 with what charge? -2, right? So the formula here would be what? CaCO3. Okay, this 3 here, what does that tell me? This 3 tells me that cobalt has a charge of +3 or 3+, right? A lot of students, even on the final, will think that that 3 means that it's a subscript of 3. And that's not correct. Okay, that 3 is telling me that it's a cation with a +3 charge. What's nitrate? NO3 with what charge? Minus, right? So this is CO what? NO3, 3. Okay, this 2 tells me that copper has what charge? 2+. And what's phosphate? Phosphate is PO4, what charge? What's the charge? -3. So what's the formula when you crisscross? It would be Cu3 PO4 2. Do we agree? All right, lithium has what charge? Li plus, and sulfate is what? SO4 with what charge? -2. So this is Li2SO3. 4. Oh, right, that's sulfate. Sulfate, not sulfite. Questions on 12? All right. Now we're going to do some naming. What's the name of A on 13? Right, good. Iron 3 sulfate. Right, because you uncrisscross them to figure out what the charge there is. What's the name of B? Good. Aluminum hydroxide. And what's the name of C? Nitric acid. Good. All right, questions on 13. Let's move on to 14. All right, an experiment uses 4.89 moles of aluminum. What mass of grams in grams of aluminum is this? So we're converting moles to grams. So 4.89 moles aluminum. What do I use? Molar mass, right? Aluminum's molar mass is 20 something. 26.9815. Grams per 1 mole. How many sig figs am I keeping? 3. 6.9815. 3 sig figs. I got 131 grams. Did you? Oh yes, it is 131.9. You're up. That'd be 132. Questions on 14. 15. A lot of things being asked of me in number 15. So let's zoom it out so we can read the whole problem. Good news is 15's the last one that we're doing today, right? 15 grams copper 2 chloride reacts with excess sodium nitrate. Write a balanced equation. Okay. Copper 2 chloride has what formula? CuCl2. And what is sodium nitrate? NaNO3. Good. What are my products going to be? Well, be careful. CuNO3, 2, right? Because this is copper 2, so it's going to stay copper 2. And what's my other product? NaCl. This is AQ. This is AQ. All right, so if you were doing this reaction in lab, it would technically be no pair reaction, right? Because that's soluble as well. Is this balanced? What do I need to do to balance it? Do I need to make a reactant product table or can I just do it? All right, so let's see. We need a 2 here. And where else do we need a 2? NaCl. All right, so what type of reaction is this? This is double displacement. What is the theoretical yield of the product that contains copper 2? Now, if you were doing this in lab, it would be no apparent reaction. But let's just pretend that this is a precipitate that we could extract. And it's 15 grams. It says excess, so what does that mean? You've got plenty of it, right? So do we have to do stoichiometry twice? Nope. So here we go. 15 grams CuCl2, molar mass. I can't remember all the decimal places for copper. 63.546. All right, 134.446. Those cancel. So 15 divided by 134.446 gives me 0.111569 moles CuCl2. Mole ratio is 1 to 1. right? 1 mole CuCl2 for every 1 mole CuNO3, 2. So my number doesn't change, just my units. Now I've got to calculate the molar mass of this. Let's see. What are all the decimal places on copper again? 63, 546. 187.546. So times 0.111569, 20.9243, keeping 2 sig figs, right? So it'll be 21 grams. If you obtain 27.3 grams of the product containing copper 2, when you actually do the experiment, what is your percent yield? How do you calculate percent yield? Right, actual over theoretical. This is the theoretical. Actual is 27.3. Theoretical is 21. We're going to multiply by 100, right, because it's a percent. So 27.3 divided by 21 gives me 130%. So, how would you explain this? It's not possible to have a percent yield greater than 100, right? The max value it should be is 100. So what happened? Some sort of experimental error happened. What is it? Well, you could have extreme contaminant. Like we're talking, you know, you're using your beaker that you just, you know, barfed into. So, I mean, that would be, because you'd have to have an extreme amount of contamination for it to be 30%. But I mean, yes, it could. It could be contamination. What's the more likely scenario, though? Let's pretend that this was a precipitate that we filtered and then dried. What would be? Like we didn't filter enough out. No, that'd make your yield lower than 100. What if it wasn't dried all the way when you put it on the balance? That'd make it too high, right? Just like if I say, all right, guys, sometime in the next 24 hours, stand on the scale. Are you going to do it wearing your backpack and your shoes and carrying your purse? No. Right? You're going to do it at some point where you've got the least amounts of stuff, right? So you've probably got water in there, most likely. Contamination would work. It'd have to be pretty extreme contamination, though. All right, so that's where we're going to stop for today.